Hello everyone, and thank you for choosing to spend this lovely afternoon with me and Linux booting and hardware management. My name is Karol Przybylski, and now that you have seen my face, I will go safely off the camera so that you can focus on my presentation. Okay, so first of all, once my presentation starts working, let us go to the very short who am I. So my name is Karol Przybylski and I work as hardware integration engineer at Nokia, involved in a team in hardware verification of Nokia 5G modules. I like embedded hardware and software, and I'm also Times Person of the Year for the year 2006. If you don't believe me, go ahead and Google this. Also, you can hit me up on my email if you have any follow-up questions or anything like this. And now, since I share my name with the famous Polish comedian Karol Strasburger, let's start with a joke. So, happy 25th birthday, Linux. Here's your effing cake. Go ahead and compile it yourself. And I think this joke actually encapsulates a lot of our feelings about Linux and how we love to hate it. So, we have our joke out of the way, and now let us list some units for today's webinar. So first of all, we are going to talk about Linux boot process, an overview of the process. Then we will have a short initramfs demo. Then we'll talk about hardware representation in the system from user space point of view. And then we will create a simple but fun kernel device driver followed up with some demo. And important thing to notice is that content will be focused around embedded devices. And since we are talking about embedded devices, embedded Linux, then of course the main architectural choice is the ARM architecture. And also some disclaimers. So the content that I will present to you today will be somewhat simplified because every single of the topics that I will be talking about could take weeks in order to learn it properly. So there will be some simplifications, but I will do my best. Also, there are various ways to success. We should remember about this in our daily life, but also when we are working with Linux. So there's 1,000 different ways to achieve the same goal. Here I will present you one of the ways, the most popular, the most general one, but still one of the many ways. And also I'm just a dude hosting a webinar. So question authority, you know, I like working with Linux. I know some stuff about it, but still it's such a broad domain that there might be some mistakes. If they are, please point it out in the chat and maybe we will all learn something. So now to the meat of the presentation. Here I have compiled, after very much work, a one slide diagram for the boot process. So first we begin with pushing the power button, then magic happens, then we have a running system. And even though I know some stuff about Linux, obviously I prepared this presentation about boot process still, it sometimes look like magic even to me. But let's go ahead with the real overview of the process. So everything starts with power on, and by power on, I mean power on reset. And what is power on reset? Because this is the biggest reset that you can get. Everything is reset to its default state. Because it might happen that some part of the system is reset, like one of the chips of the processor, some other FPGA or whatever. But we are not talking about this. We are talking about real power on reset. Usually it's done by plug in and plug out of the power lines to the module, to the board. Okay, then the first phase is the ROM code, usually embedded in the silicon. Then we have the secondary program loader, which is usually U-boot. Then U-boot handles control over to the kernel. Then optionally, we can have a early user space, which is called initramfs. And then we have our init process, our login prompt, and the system is fully usable. And actually, before we even get to the ROM code, we have to remember that it all starts with CPU executing instructions. So how does CPU look like? Well, it can look like this. And actually, when I'm talking about the CPU, I make a little shortcut of my thoughts, because nowadays CPUs, SOCs, whatever, are extremely complex devices. So usually when I'm talking CPU, someone else is talking CPU, we are talking about the whole system that is responsible for executing of the instructions. So now let's examine how CPU executes instructions. And we have to remember that CPUs and computers in general are not very smart. In fact, they are pretty dumb. All they can do is calculate things quickly. And when I was studying at the university, I was taught by the teacher that actually CPUs can only do three things. First thing is fetch an instruction. Second is decode an instruction. And third is execute an instruction. And this goes on and on forever, basically, nothing else. And whether the instruction is smart or not, whether our system is doing something interesting or not, this is up to the system and the programmer who is programming. But those three steps are not all, obviously. You also shouldn't forget about the fourth step, which is memory access, and the fifth step, which is register write back. Those are not happening always, but still they are happening most of the time when you are working with memory and registers. So the full cycle looks like this: fetch an instruction, decode an instruction, execute an instruction, memory write back, and register access. 5 steps to glory. And when you have all those steps lined up, we can introduce something which is called instruction pipelining. So not every subsystem is equally engaged in every single step of this. So for example, when we have something like arithmetic logic unit, which is responsible mostly for calculation, this subsystem is not really engaged in fetching an instruction. So while one thing is executing an instruction like allo, another subsystem of the CPU can be handling memory writebacks or instruction decoding. So this is the way of introducing a sort of parallelism into the execution of instructions by the CPU. At the same time, all of the CPU subsystems are engaged in action, and each one of those is doing something else in order to speed up the execution. And of course, this is simplification because modern systems are way more complicated. They do way more stuff, and this is just the overview. Okay, so once we have the execution of the instructions covered, then we can go to the stage one, which is the ROM code. And this is the first stage. Usually we don't have much control over it. It's embedded in the silicon by the vendor. And what resources do we have? Well, we have one CPU core, usually, and some on-chip static memory. Usually it's some kilobytes of static random access memory, not much, but it's the first step. And our mission is to load the secondary program loader into the memory and perform some necessary inits, which might be phase locked loops, system clocks, watchdog timers. Watchdog timer is very important for the stability of the system. And if we are loading it at this point, depends on the configurations and of course the vendor's mercy. Also, we have few boot types which we can control. We can have flash boot, SPI memory boot, eMMC boot. So it all depends. And also, if you can remember the diagram that I showed a few slides before, we have a boot ROM even outlined here. This is not a thing that we can usually manipulate. It's just supplied by the vendor and we can control it. And how can we control it? Well, mostly the control is done by hardware because at this point in the system's life, we don't have much software and we have to control it by hardware. So usually it's done like this. We have some soldering pads in here. This is taken from some Texas Instrument CPU, the whole board. And usually we have also deep switches. So in here we have deep switches numbered from 0 to 15. And depending of the configuration of those deep switches, we can choose if you want to boot from the SPI memory, if you want to boot the FPGA or not. It all depends on the vendor specification. Okay, so we have more or less the ROM code covered. Then let us go to the secondary program loader. So there is some discussions about what is the secondary program loader and what is the tertiary program loader. And once again, this is highly product dependent because there might be another proprietary blob which handles memory initialization. For example, in the Raspberry Pi, there is no U-boot or anything like this. There is something called bootcode.bin, and this is handling initialization from the ROM code up to the kernel level. So it's different, but usually it will come down to running the full-blown bootloader like U-boot. So after the ROM code, U-boot takes control and finishes the initialization. And what are the objectives of U-boot? Because U-boot is the most used one, the most popular one. So we need to set up the rest of the needed RAM, because at the beginning we set up some portion of the memory to load U-boot, but not the whole memory. So we need usually way more memory in order to load the kernel. U-boot also has to set up the device tree. What is the device tree? Well, this is a flexible structure that's used to describe what hardware is connected to the board, basically. It's pretty flexible and widely used nowadays. Also, another objective is decompressing the kernel. However, this step is actually optional. Sometimes the image of the whole kernel is already supplied, and this step is not needed, again, depending on the configuration. And finally, the U-boot has to load the kernel into the memory and then handle the control over to the kernel. Okay, so what can we do in U-boot? Well, usually we have a magic device like this connected to our board. This is the USB to serial converter. And usually it's the only way to talk to U-boot, because at this point, usually there are no network interfaces available. We can't really do much stuff. And the serial interface allow us to do some early stage diagnostics. And what can we do else? Well, we can set and get environment variables like this. We can set an IP address early if you want, for example, to perform some network booting. We can also read and write memory regions. We can even load the whole kernel into the memory and see what happens, see if it loads and so on. Also, we can download files from network if we want to perform a netboot or PXE boot, like it's called in the Intel world. And also we can perform some diagnostics. Usually, again, depending on the system, maybe you have some early stage scripts which will check if the hardware is connected and so on. A bit like power on self-test. So I was talking about U-boot for a good while, but we could think for a minute why U-boot is the most popular solution out there. So first of all, it is open source. Usually when something is open source, it can gain a big popularity among other people, and Linux is also open source, so it's a bit of maybe tradition of popular products. Also, it supports a lot of architectures. If you go to the U-boot repository on GitHub and you will go into the arc folder, and then you will find basically every single architecture known to humanity. That a lot of stuff is supported right from the start, so it's easy to get it running quickly. Also, it's highly configurable. You can tune it to your every single desire. In most of the commercial products out there, it is used. And also there's a vibrant community. Now the code review process is maybe long, but it's really, really thorough. There are mailing lists where you can ask a lot of questions and get an answer very quickly. But I have to also mention some of the alternatives to U-boot. So for example, we have Barebox, Grub. Grub is mostly used on desktop distributions, and also Little Kernel if you want to have a small bootloader. And more information, of course, can be found on the U-boot GitHub page. And now let's talk a bit about how does it feel working with U-boot, because I had some pleasure of working with early stage bootloaders. So this is actually stuff that I was doing a while back, spending some hours in the lab, because I work in R&D, and as it is in R&D, usually sometimes the board are bricked and sometimes you can't get it up. The serial interface is not working. And what do you have to do in this situation? Well, you have to go to the laboratory, hook up your SPI programmer and upload the new image. Also doing some more tests and some more verification. So in here we have something called the dediprog. This is the SPI programmer. This part is connected to the computer when I would have my U-boot image with me ready, and this is connected to the onboard memory, and that's how it goes, downloading images, uploading them, checking if everything is okay. So I like working with hardware. I like knowing how stuff is done. So I can say to you that it's usually pretty annoying because it's trial and error, R&D, lots of unknown stuff, but it's pretty satisfying, and I quite enjoy it. Okay, so now that we are finished with the U-boot, the U-boot is handling control to the kernel. And what information is passed from U-boot to the kernel? Well, a basic information of the hardware detected so far. For example, clock speeds. Clock speeds are extremely important, so the kernel would like to know which clock speeds to use. Also, there is passed something called the kernel command line, and usually it looks like this. So this is a simple string which tells usually a bunch of useful information. For example, where the serial console is attached. Where the serial console is basically a must when working with embedded systems, because network connectivity is often something not available. Also, on which virtual terminal the console is attached, where should we mount the root file system, what is the type of the root file system, and so on and so on. Usually there's a lot more information, but depends on the configuration. Also, we are passing the device tree information, so basically any information about the hardware. And if the device tree is not available, then we can pass the machine number, but that is a bit obsolete right now. And optionally, a initramfs location in the memory if we want to boot using the initramfs. And also, what does the kernel do at init? Well, it does a bunch of stuff. So it's setting up interrupts, signals, architectural stuff. Again, everything that you basically use in Linux has to be set up by the kernel. And finally, it looks for the init process, or it mounts initramfs if we desire to boot with it. And usually we can see this beautiful piece of log booting Linux on the physical CPU. And actually, because kernel is a open source project, you can easily see what is happening when in the code. So let us now examine what is happening at the kernel code. Okay. So here we have a Linux repository. As you can see here, GitHub, Linux master, and the folder is init, and the file is obviously main.c. And in here, we could ask ourselves a question: which function is starting the kernel? Well, function start kernel, obviously. And it does a lot of stuff, and I will not go through it all because we don't have that much time. However, as I have mentioned earlier, that the command line parameter is passed all throughout the system. This is also happening here, and a lot of things are getting the command line. And like I said, for example, it disables the local interrupts because we don't want anything messing around with our initialization, signals, interrupts, so on. And it also does the architectural setup, because different architectures require different stuff. So let us now go to the architectural setup. So here you can also easily examine this if you are interested. So when you go to the Linux repo and go to the arc folder, and there ARM64 kernel setup.c. We have setup arc, and as you can see, it's pretty easy to get around in here. Of course, these functions do a lot of stuff, but thankfully some of them are actually commented, and you can find in here a lot of useful information if you want to understand the boot process better. Okay, let's go back to the presentation. And now at the end of kernel, we might have a initramfs stage, so early user space. So let's start with the definition of what is initramfs. So it is a CPIO archive attached to the kernel, which acts as initial root file system and handles some of the initialization procedure. That's basically it. If you are wondering what is CPIO, then basically it is an ancient tar, ancient archive, and it is widely used in the desktop distributions. I think in all of the major ones, and also in the bigger embedded systems, because it provides a lot of flexibility, but more on that later. But of course, you can just skip it completely and go mount the root file system and go straight to the init process. Okay, so now we will have a little demo about initramfs, because I think that initramfs is one of the underrated things when it comes to the boot process. So I hope it will be interesting for you to examine it a bit further. So we will learn about some tools used to create the custom initramfs and see how it impacts our booting. Okay, so now let us go to the demo system. And in here, I have my old trusty Raspberry Pi, which will perfectly fit our purpose. So I am already logged as a root. You can see what system are we in. This is basic stock software version that you can get for the Raspberry Pi. And let us see now what is the current boot time of the system using this very handy command. So we can see now that the startup is happening in the 4.8 seconds for the kernel and 37 seconds for the user space. Please remember those numbers, they will be useful later. So now we would like to, and now the system is by default not booting with initramfs. In Raspberry Pi, it is disabled by default. So how can we create our own initramfs? Well, there is a tool, mkinitramfs. And what is this? Well, low-level tool for generating an initramfs image. So without going through the boring details, let us now create a initramfs image. Okay, -o for the executable name. We always want to be the gunzip, and now we have to also specify the kernel version that we are using. Okay, and we are doing the smart way, so that should work. Okay, so now we are generating the initramfs image. This will take a short while. So I'm using Raspberry Pi on the stock software, and many of you could say that, you know, Raspberry Pi is not a real embedded system. And with the stock software and stock configuration, I would actually agree. Because embedded systems by default are usually single purpose or few purpose system. And you know, on Raspberry Pi, you can basically run Minecraft and do whatever. Nowadays, there are acting more as personal computers than embedded systems. But if you buy a version that does not have an SD card, but it has eMMC memory, and you tweak it, and maybe you create your own distribution using Buildroot or Yocto, then you will obviously have an embedded system. So if you are not familiar with them, then Raspberry Pi is a very, very good starting point. Okay, so we are done with the creating of the initramfs image. Let us see for sure if we created it. Yes, looks about right. So this is the image generated by us, but that's not all we need because we need somehow to enable it. And how do you enable something in Linux? Well, you need to modify some file. And which file should we modify? config.txt, obviously. Okay, so let us do just that. In the boot directory, there is a lot of interesting stuff happening. So let us modify config. Okay, at the bottom, I have this line. And when I uncomment it, it will basically tell the system to boot using the initramfs. And the first command is obvious. It tells the configuration manager to mount initramfs. Then we are specifying the name of our image. And then we have an instruction called follow kernel. So what that means is we are telling the system to put the initramfs image in the memory right after kernel, because this information is later used by the kernel in order to load it. Okay, I think we can close now. And also let's do a quick check. We did it all right. Okay, also sync. Yes, so now let us go to reboot the system and see if the demo worked. Okay. Yeah, we have to wait a short while, and I actually also have ready my old trusty serial connected to the board. Because like I said, if you are working with any sort of embedded systems, then serial connection is absolutely necessary, because if you don't have the access to the network or anything else, then serial connection is the only thing that you can use to examine the system, talk to U-boot and other stuff. Also, when we are talking about the embedded boards, obviously there are other candidates good for, let's say, basic embedded systems. I've heard good things about all-winner boards. And also, like I said, not everyone realizes it, but actually Raspberry Pi Foundation is producing industrial versions of Raspberry Pi. And I think those are pretty useful in the industry. Okay, so now it seems that we have booted. So let's try to connect again via the network. Okay. My very secret password. And we are in. Okay. So let us now check if the initramfs was indeed used. We will use for this journal. This command basically displays the journal from the last boot. And now let us search for the keyword. And yes, here we can see that the kernel is telling us that he's trying to unpack root.fs image as initramfs and then some additional stuff. So yes, indeed, we are now booting using the initramfs. It wasn't too hard, but then we are using the basic image. So now let us, oh no, no. Okay, I can't use Ctrl+L to clear my screen, because then the WebEx tells me that it will throw me out. So I have to keep my screens dirty. Okay, let us see what was the impact on booting, and maybe you remember or maybe not what was the time in the previous example. We had a little over 4 seconds, and now we have more than 13 seconds for the kernel. So why is that happening with initramfs? Well, we could say that it's pretty obvious, because right now with this image, with this setup, we have basically added another step in the initialization. So we didn't bring any benefit. Basically, we have just added another step of the early user space initialization in initramfs. So in order for this to be useful, we would have to recompile the kernel and then use initramfs. Because for the Raspberry Pi, this is, system directed for the beginners. So the kernel is initializing everything it can, every single module. And in normal system, you wouldn't do that. In normal system, the commercial one, You want to have the kernel as small as possible, to do as little stuff as possible, and then handle the control over to the initramfs, but more on the benefits will be a bit later. So if we want to examine the initramfs further, we can use a tool called Dracut. It's not readily available for the Raspberry Pi, but you can easily get it. And this is another tool for generating initramfs image, but it has more possibilities. It's way more robust than the basic tools. And using Dracut and the Dracut modules, we can actually examine what is inside initramfs. So now let us create a temporary directory. I will also have to become super user to do this. Okay. Okay, and now I can't use my shortcuts because WebEx will scream at me. Okay. And now if you use the top secret command that we have right here, we can actually unpack the init ramfs and examine what is inside. So we are using skip CPIO. This is a tool supplied by Dracut, which allows us to recursively analyze the CPIO archives. We are then taking the initramfs.gz, piping it to the gunzip and then to the CPIO in order to have it available. So let us just do this right now. And I will stress it again that we are not using a lot of configuration. Normally, if you want to ship the system, you would do way more configurations to make your initramfs as lean as possible. And now if we go with ls, then you can see that it resembles a bit the root file system. And indeed it is. initramfs is a root file system, but smaller, used to do some early initialization. We can even do 3 here, and we will easily notice that there's a lot of similar stuff. And if you want to save the command, then after the session, I will send you the commands that I used. So if you are doing screenshots right now, then you don't have to do it anymore. I will send you everything you need. Okay, so that, oh, there's also one more thing. We can easily see what is in our initramfs by using tool ls initramfs. And if you use it, and wait a bit because this is Raspberry Pi Zero, which is pretty slow, then you can see how many modules, how much crap this image has inside. Obviously, we don't need so much of this, but this is just for the example purposes, just so you can see what is this inside this early initialization code. Okay, so this concludes the first demo. We can go now to back to the presentation. Okay. Okay. So let us now recap why would we bother with the initramfs? Because obviously, since everyone is using it, it has to bring a substantial benefits for us. So when we are using minimal kernel and then initramfs, the customization of the boot process becomes much easier because we are moving code from kernel space to user space. And kernel space is powerful, but it's generally better to write code in the user space because it's safer and usually it's simpler. And also we want to simplify the kernel logic for initialization. Back in the day, I don't know, I think 15 or 18 years ago, where initramfs was something new, then there were a bunch of dirty hacks in the kernel in order for it to boot properly, and initramfs simplified it a lot. So those are the main benefits why the initramfs is used. So let us now quickly recap what we have covered so far. So we went through the phase of the ROM code, then we went to the secondary program loader U-boot, then we did kernel initialization, initramfs, and finally the init process. So now question to the chat. What is the PID of the init process? This question is actually sometimes asked at the interview. And usually people get it wrong with two numbers that look like something that could be the init process. But yeah, simple question, but I've seen it a bunch of times already. So after answering the question, we can learn what is the init process or system. So basically, an init process is an operating system within an operating system because it does so much stuff. The main quest of this is spawning all of the other processes. In simplification, mostly using syscalls like fork and exec, because init process is the parent for all the other processes in the system. And it also manages user space services. It's pretty complex. So like it was said, an operating system basically because it gives us a lot of possibility. And what types we have of the init process? Well, the most important one nowadays used in most products is the systemd. Back in the day, I think 10 years ago, the sysv was standard. Sysv was the stuff that had the run levels and daemons. Systemd has services and timers, but it also carries the compatibility with the older legacy systems. And also we have something like BusyBox. BusyBox is the default init system for the images generated by the build root. It's very, very simple, but thanks to being simple, it's very, very easy. And on the other hand, things like systemd are incredibly complicated. And they also gather some hate among the Linux community, which some people think it's too complex, but it gives you a lot of possibilities. Okay, so after init process, we have our login prompt. We can log in as users, use the system, so mission is completed. Now kernel goes idle and waits for the system calls from the applications. So now we can proceed to the second chapter of our journey, so the hardware management. We are logged in, we have access to the system, and now how do we get to hardware? And we have to answer the question, how is hardware detected by the system? That's a pretty important question. And actually, there are some types of hardware detection. Usually, like in most things, you can do stuff automatically or statically. So the first automatic tool used for hardware detection is UDEF. I think most of you has met with UDEF because of the UDEF rules, which specify what should our system do when we are connecting new hardware to the boards. And basically it works like this, that hardware events are generated by the kernel, and then UDEF catches them and performs whatever initialization is required. If you want more, then I recommend you to read man pages for UDEF. A lot of interesting information is there. We also have something called the ACPI. This is a framework used for the firmware of the devices. Basically a framework that allows talking between the firmware of the devices with the main system, but I cannot go into much detail because I think the specification for the ACPI takes like 1,000 pages. And even our best buddy, Linus Torvalds, says that ACPI is a complete design disaster in every way, but we're kind of stuck with it. But be aware that it exists. And also we have static types of initialization. So we have the device tree, like I said, flexible way to describe the hardware connected to the board. We also have something called the platform data. Platform data now I think is a bit obsolete because the device trees are taking over. The platform data is basically a set of C structures directly implemented in the kernel modules which describe the hardware. We also have the buses with query abilities like PCI and USB. They were built with the being hot plug in mind, so they have the query abilities. And of course, we can insert our modules manually by scripts, by hand, whatever. And now let us go to the hardware representation. So let's turn for a while into Linux kernel developers and think, how would we design a system an interface for hardware available to the user, keeping in mind that we do have a few constraints in here. So first of all, full control can break the system. So we shouldn't give full unwarranted control to all of our users because kernel space is powerful, you can break the system easily. So it has to be somewhat constrained. Also, dealing with hardware can be pretty overwhelming because some small embedded boards like IoT system sensor are pretty easy. There's architecturally easy. There isn't much stuff connected to it. They have to be small because of some other things like power consumption. But if you go to the bigger embedded project, then you have a lot of hardware from some R&D projects or whatever, so it can become pretty complex very quickly. And also we want to have our representation standardized as much as possible because we want an experienced user to be able to learn some API pretty quickly in order to be able to use the system and hardware efficiently. And of course, we have to remember that in Linux, everything is a file. So how can we control something in Linux? By files. And here comes our next hero. So that is sysfs. This is a virtual file system that is used to control the hardware. And I think this excerpt from the man page encapsulates it pretty well. So it's pseudo file system which provides an interface to the kernel data structures. So whatever the kernel has defined as hardware data, then we can access it in sysfs. And we have some directories there. Obviously, there's a lot of them, but I will cover the most important ones. So we have sysclass, which takes all of the classes of the devices registered by the kernel. We have also sysblock for block devices. There's also sysdevices, which has all of the global device hierarchy in the system. And also the sysbus, which refers to the physical bus, like for example, I2C and so on. I2C widely used in embedded systems throughout the world. Okay, so a careful watcher of this presentation might ask a question, what about proc file system? And that's a very good question, because the proc directory is the old legacy directory. Back in the day, when I think I didn't even know what Linux is, there was only proc directory in the system, which had all of the stuff related to the process table and all the other things related to the hardware. But with time, it started getting messy, too much stuff, cluttered. So Linux developers decided to introduce another directory. And also proc focuses mostly on process table. So if you go to proc, then you can find the directory with every PID in the system, check some stuff and do some configurations. And sys focuses mostly on hardware. If you want to do something with hardware, then usually you will have more capabilities when you are in the sys. And of course, some functionality is overlapping for the legacy reasons, for all the other reasons that I don't know about. It's just legacy. There is a lot of overlap. There's a lot of stuff that you can do both in proc and in sys. Okay, so now let us go to the second demo where we will shortly examine the sysfs capabilities. Okay, so let us go again to our demo system. Okay. So now there is one file I would like to start with, which is actually in proc, but it gives us a very nice list of all the devices connected to our board, alongside with the major numbers. What are the major numbers will be a bit later. So in here we can easily see all of the character devices and all of the block devices connected to our system. So this file from the start gives you a very nice overview of what you have available. And now let us go to this sys directory. Okay, and let's do this. So from the output of this tree, you can see that this directory is pretty complicated. And even though we do not want to be it overwhelming, well, it pretty much is. And how to learn it? Well, mostly by trial and error and also reading kernel documentation, which can sometimes be challenging, but this directory gives you those 4,500 directories, gives you a lot of power over the hardware that you have at hand. So now let's learn some useful stuff about the system. Okay, let's check what do we have here. So let's go to the class. Now let's go to the net. And in here, as you can see, Raspberry Pi, pretty simple. Normally in bigger embedded products that do something with the network, then you would have a tens, if not more, of network devices. But in here we have this loopback and LAN 0, which is responsible for my Wi-Fi connectivity. So now let's say that we want to know which kernel driver is used by the Wi-Fi chip on my board. And there's actually a few ways to do this. We can do it like this. We can go to the directory, we can do ls, then we can go to the device, can do it again. And now, because what I have to also mention that the structure of the hardware is defined in the sys directory by symlinks. Usually, so the symlinks tells you where everything is connected, but sometimes they are not easy to read. So we can use a handy utility in here in order to list the driver. And there we go. We can see here that the driver that is used by the LAN 0 device is some Broadcom driver that is with the Wi-Fi. Okay. There's also another way to do this, and that is using UDEF utilities. So we can do this. Info. Okay, and this UDEF adm info gives us a lot of interesting information. And in here as well, we can see that the network driver is following. I recommend you to read more about this utility because it comes pretty handy when dealing with the devices. And this is what the symlink would tell us. So this is some data about PCI connectivity, but from the start, when we look at it, it doesn't tell us all that much. Okay, so let us now perform some practical example with the LED. Okay, let us go to again to the class. Now to the GPIO. So normally you would control GPIO from some C program or C++ or Python, but actually you can do this also from the sysfs. And how would we go about turning the LED on? Well, I actually have with me the LED, and if my camera works, then I hope I will be able to show it. But this is the task for now. We want, using sysfs, turn the LED on. So now what we have to do is we have to export the pin. We have to tell the system which pin do we want to use. And I want to use the pin 21. And now I can put it into the export. And now that I have given the system this command, we have a new directory called GPIO 21. So let us go there. Yes, and what we have here? Well, here we can do some setup that is typical for the GPIOs. So set the value, set the direction, edge power, whatever. We will just do the very simple one. So let us first decide the direction. So I want direction to be out because this is an LED. To the direction. Okay, that has worked. And now to the value. And now I will turn my camera on in order for you to believe me that I have actually succeeded. I hope my camera will work. Does it work? Okay, so now when I execute this command, this LED should light up like never before, and it did. So we have just controlled the LED using the sysfs. And if I do 0 in here, then it will go back to being dark. Okay. So as you can see, sysfs gives you a lot of possibilities. And in order to clean up the mess that we have just did, we have to write echo 21 to the annex port, and everything is as it was before. And also one thing I want to mention is the sysctl utility. The sysctl is a command line tool that can be used to access some of the hardware properties. And if you do -8, then you can see all of the properties that you can control. Some of them are related to the process table and other are related to more of the hardware stuff. So I recommend you to give it a read. Okay, back to the presentation. Okay, so I mentioned major and minor numbers before. So let us now go to maybe a bit more depth of the subject. So if we do ls in the ls -l in the dev directory, then we will get a bunch of interesting information. So first of all, we can see those letters which describe if this device is character or block device. Usually most devices are character devices. There are some kernel insights differentiating both of them. And in here we can see the major number and the minor number. And major number is the driver associated with the device. So with this device media 0, we have associated driver with the number 240, and with this device another number. And minor numbers are used to differentiate among other devices. So for example, those two things, media 0, media 1, are using a driver with the number 240. But in order to differentiate, one of them has to be 0 and another one has to be 1. And that's basically it. Pretty handy. If you want to, I couldn't find the mapping of the major numbers easily in the system. You can grab the kernel modules for it, but I believe that on the kernel pages, there is some mapping of the major numbers to the devices. Okay, so my presentation about managing hardware wouldn't be full without speaking a bit about kernel device drivers. So what is a kernel device driver? Device driver is a piece of code that talks direct with the hardware. It provides an interface to the device for the users to use and for the system to use. And there are some things important to remember about the drivers, that they only do what is essential, nothing else. They have to be as simple as possible, because working in the kernel space is difficult, it's dangerous. So we are doing only what is essential, and then some higher level algorithm can be implemented by the application. So for the recipe for the kernel module, kernel device, we can take the algorithm from the vendor's datasheet, how to use their hardware. We can mix it up with some C code, because kernel development is done in C. Then we also have to know a bit about the kernel API and kernel libs, libraries, not liberals. And then we have our kernel module. And we should do as much as possible not to write one yourself, because usually it's better to use syscalls. It's safer to work in the user space. So, and unless you have some very, very new hardware, you don't actually need to write one on your own. So let us go to the last demo where we will try out some basic kernel devices. So let's go again to our Raspberry, and this time I will need the two windows. Okay. Okay, so on my GitHub, I have some examples of the kernel device drivers. A link to those will be supplied to you after the presentation. So I need to become the super user in here and go to have some fun with the drivers. So we have two examples. First one is very easy. Then the second one is a bit more advanced. So now let us proceed with the easy example. And in here, I would like to see the kernel buffer. Okay, so let's watch for some fun kernel events, and let's go to the easy peasy directory. And I have some C code in here, so let me just do this in order to compile all of that. So one thing that is maybe a bit deceptively easy about kernel development is that it's pretty easy to write the make files, at least in the basic examples, because we are handing over control of the build process to the kernel build system. This is, I think, one of the simplest make files that you can get. We are basically calling the kernel's build process, so there's not much hassle. Okay, so now we have compiled our kernel module. Let us insert it into the system. Okay, so I would like now to insert the insert module, Linux kernel module example.ko. .ko means kernel object, and it is generated from the .c file. So when I insert it, some interesting stuff has happened. So we have now the information on the console that we are loading an out of tree module which taints the kernel. That doesn't sound very good, but it's actually very true, because we have just inserted some out of tree kernel module. So out of tree meaning some module that the user created and it's not verified by the community. And what are the consequences of that is that if I would like to have some help from the Linux community, they would ask for my kernel signature or whatnot. And if they would see that I'm using the tainted version, then they would not help me because I did some kernel space stuff, and I have to fix it first. And then after this communication, we have hello world. So every first sentence that every programmer speaks. So now let us examine the code. And that is .c file. Okay, it starts here. So it's at the start, it looks like regular C files. So we have a bunch of includes to the kernel API. Then we have a bunch of macros used for the administrative stuff. So license, author, and so on. And then one thing that comes to mind that there is no traditional C main function. Instead, we have init function and exit function, which are later declared to the kernel as module init and module exit. Nothing more. This is the simplest stuff that you can create. Basically, when we are inserting the module to the kernel tree, it prints the hello world, and then when we are removing it, it prints goodbye world. That's it. That's pretty easy. So let us now remove it. Goodbye world. The module is gone. So now let us do something more interesting. Okay, this one. So let us make this again and watch the magnificence of the very hard to make file. And in this example, we will have some more fun with the device files. We will actually create a device file. So let's insert it into the tree. That KO. So module X is loaded. I couldn't think of a better name for this. I didn't want it to be test or something like this. And actually it created a device file in the dev directory. So we can now list for it. And yes, indeed, we have a character device created with the major number 42, because this is the answer to the world. And here we have dev mod x0. So now we can, what can we do? Okay, so now, for example, we should examine the code that actually makes this stuff happen. So that C. Oh, I should put it to less. Okay. Okay, it starts here. I'm sorry the display is so cluttered, but you know all the complaints go to WebEx because I'm unable to clean my terminal. So now we see the same stuff that we've seen before. So a bunch of includes. Then we define the device name. We also defined the major number that we have just seen in the ls-l. And then after some also basic initialization, because this module is actually at the init, it lights up the LED, and at the exit, it turns it down. But since you have seen already my LED going on and off once, then I assume you will believe me that it works. Then we have a bunch of functions, and in here, if we want to write a kernel module that deals with the device files, then we have to define a structure called file operations, which deals with the file operations performed by the user on the file that we have just created. So we have to specify the owner. Well, this is basic, this module. And then we are defining the callbacks to the functions which are happening when we are opening the file, releasing the file, reading and writing. Obviously, there's a lot of more options available here, but this is the basic example. And then if we are going to the initialization of the module X, we are registering the character device using some kernel magic. Then we are creating the class of the device based on some given information, and then we are creating the device. And also, just for fun, I added some code that would turn on the GPIO. So first we check if the GPIO is valid. Then we are requesting the GPIO from the system because maybe it is occupied by something else. Then we are changing the direction output of the LED, which automatically will turn it on once it is exported. So as you can see, those are basically the steps that we have done when we were dealing with the sysfs. And when we are in the exit function, which is then registered here, we are destroying the device, destroying the class of the device, unregistering the device, so basic cleanups. And then we are going with the LED to what it was before, so unexporting and freeing. So now that we have this, we can quit, and now we can write some stuff to the device. So maybe it would be better. Okay, so now I can actually write to the device file. And there you go. The kernel ring buffer, which is read by dmask, actually called a function open, then write, then release. And what it wrote, well, basically the number of characters written to the file. And I also can read the file if I would so desire. But then it basically reads some gibberish, but you can directly see what the functions are called and when they are called by the system when you are using the module. And if you want to examine those examples further, then there will be a link to my repository. You can download it, make, insert, whatever stuff you want. And obviously those examples are pretty simple, but then if you want to have more functionality, do more stuff, then it becomes more and more complicated. And remember that in kernel space, we are very, very powerful, which can be sometimes our curse. So now, last but not least, let us remove the module that we have just inserted. And yes, module X going down. Okay, so this concludes the last demo that we have. We have still some of the presentation left. So some debugging tips if you are working with the Linux or you want to work with the Linux. So there is some tips. So first of all, you have to be aware of the commands that you can use to control the system. lspci used for the devices using PCI bus. DME decode, this is used for interacting with the U-boot, with bootloaders. Then systemd udevd, I recommend you to read the man entry for this because it provides a whole bunch of stuff that is used for the hardware, and then udevadm, which is also pretty useful. And then when it comes to kernel development, especially, you can find a lot of information on the internet. But what is bad about finding information about kernel on the internet is that most of that stuff is way outdated. If you find some kernel device example from 2012, then it will most likely not work on the modern kernels because kernel API is constantly evolving, stuff changes. So yeah, you should always try to find the real docs, and one of the ways to find the real docs is to download them on your system, and this is the command for Ubuntu, but for every distribution you can find it easily, or just go to the kernel webpage. And also I recommend you to read more about man. You can even write man and read more about how you can use the manuals more effectively. And yeah, that concludes the majority of the presentation. So let us recap what we have covered throughout this little more than 1 hour. So we've covered general booting process, hardware handling in sysfs, and basic kernel device drivers. And now, equipped with this information, you can do whatever. You can check if there's a cat on the picture. You know, TinyML exists. You can upload OpenCV on your board, or instead you can create a spaceship using embedded Linux. Basically, the world is at your disposal.